So, hello everyone. This is the first lecture of our series of digital logic and design, which is included in the syllabus of BIM under the Tribhuvan University in the first semester. So, I am from allinOnestudy.com and this is our website. So, under Tribhuvan University, we will be going through BIM and we will be doing the first course on digital logic design, which is under the first semester. So let's go through the syllabus first. So this is the code for digital logic design, ITC 212. Here are the module objectives, contents, and in summary, in this course, what you need to know is you have to go through, or you have to gain the knowledge of the number system, various number system, and conversion between one number system to another. After that, we will be going through the complements of the binary numbers, and we will be also looking towards the addition and subtraction of the binary numbers. After that, we will be dealing with the codes, certain digital codes. They can be alphanumeric codes like ASCII, or just normal code like gray code or other codes. And in unit 2, we will be dealing with the digital design fundamentals, which include the differentiation between digital and analog quantities, their basic definition, and other things. And we will be also dealing with some of the terms like what are binary digits, various logic operation, logic levels, and basic of digital waveforms. And then we will be defining what is system and its basic concept. After that, we will be dealing with the logic gates, various types of logic gates that includes basic gates. Under basic gates, we will be dealing with AND, OR, and NOT, and we will be also dealing with derived gates, which are derived from the basic gates. And then we will be talking about the universal gate, which are NAND and NOT gates. After going through all the gates, we will be introducing the topic of Boolean algebra, and we will be introducing various formulas of the Boolean algebra, theorems, and how to use those things for simplifying the Boolean expression. After that, simplifying the Boolean expression with the help of Boolean algebra, we will be also dealing or simplifying those expressions with the help of K-map. And we will be dealing up to the 4 variables K-map only. We will also talk about the various types of expression like SOP, POS, and converting them to standard form and interconversion between them, and so on in unit 2. And in unit 3, we will start the topic of combinational logic. In this chapter, we will deal about adders and subtractors. In adders and subtractors, we will be dealing with half adder, half subtractor, as well as full adder and full subtractor. After going through them, we will talk about parallel binary adders. After that, we'll go to multiplexer and demultiplexer, their usage and implementation of various functions with the help of multiplexers. And in the same way, we will be dealing with encoder and decoders, and we will also be implementing certain Boolean expression with the help of decoders. After that, we will talk about 7-segment decoder and 7-segment display. Then we will be designing certain circuits that will convert one code to another form. For example, it can convert binary code to gray code or gray code to binary code, and so on. There are also other various types of codes. We will be also dealing with the converter circuit of them. After dealing with combinational logic in unit 3, we will start sequential logic, that is latches and flip-flops in unit 4. We will talk about basic of latches and flip-flop. After that, we will talk about the various types of flip-flops, how to trigger flip-flops, their operating characteristic, and their various application of flip-flops. In unit 5, we will be talking about the counters, various types of counters, up, down, synchronous, asynchronous, and their application. All the things will of under the counters will be described or detailed in unit 5. In unit 6, we will be talking about shift registers, So what are the various operations, various types of shift registers, and the counters which are implemented using shift registers and their implementation. So we will be dealing about shift registers in Unit 6. In case of Unit 7, we will be dealing about the designing parts. So we will first of all have some background related to state diagrams and state tables. After that, we will be using these tools that we have discussed here to design synchronous counter and the sequence recognizer up to 5 bits. Not more than 5 bits, up to 5 bits, we have to design sequence recognizer. Also, we have to analyze the given synchronous circuit. So we will be also talking about the analysis steps of given synchronous circuits. In Unit 8, we will be talking about memories very briefly. As you can see, the lecture hour, it is just 1 hour. So we will be going through memories very briefly. What are the various types of memories and basic operation, that is read and write operation in the memory. After that, in Unit 9, we will be talking about various programmable logic devices that can be PLA, PAL, CPLD, and FPGA. So these are all programmable logic devices. We will be talking how we can implement various given Boolean expression in PLA, PAL, CPLD, and FPGA. In so on, very briefly, as it is also of less lecture hour. In Unit 10, we'll be talking about various integrated circuit technology. So what are the operational characteristics, their parameter, various level of integration, and various IC families. So families can be CMOS family, TTL, ECL, and so on. And we will compare the various families in terms of various parameters. For example, it can be in terms of fan in, fan out, or operational level voltage, and so on. And talking about the lab, uh, uh, we will be doing VSDL. The course, the syllabus required that the students would be able to use VSDL language for implementing the various logic circuit which are given in the syllabus. For example, using VSDL to implement simple adder circuit, half adder circuit, half subtractor circuit, or so on. And the textbook for this course is a book by Thomas L. Floyd, which is Digital Fundamental. This is its course book. And here are also reference book. You can go through any of them. So during my course or lecture time, I will be using the content from this book, Thomas L. Floyd and Maurice Mano, Digital Logic Design. Okay, so this is all about the syllabus of digital logic that I will be going to create the videos of. So I will start from Unit 1 today. Okay, so in Unit 1, the first topic is number system, and for today's class or today's tutorial, I will be dealing with number system and the various types of number system that are important to us in digital logic design. So I will open the slide. So let's talk about number system. Uh, so number system is the system. It is the system that represents the numbers. It is also called as system of numeration. That is the system that represents number. These two are somewhat similar points. It defines a set of values to represent the quantities. Yes, depending upon the number system used, we have different set of values to define the quantity. For example, if we want to use binary, we have two values. If we go for decimal, which is used in our daily life, we have 10 different values to represent the quantity, and so on. These numbers are used as digits. Yes, these are called as digits. Many number systems are used in digital technology. The most common one are binary, octal, decimal, and hexadecimal. These are the four most common number system. There can be other number system too. If we can have base 5 number system, we can have base 7 number system, we can have any base number system. But the most commonly used are these four: binary, octal, decimal, and hexadecimal. The binary number system is the most important one in digital system. Yes, binary number system is most commonly used in digital devices. For example, in our calculator, in laptop, desktop, in during networking, data transmission, and so on. The decimal number is the most familiar because it is universally used to represent quantities outside the digital system, and it is a tool that we use every day. Yes, in our daily life, for calculating prices, for measuring purpose, we use decimal number system, and it is the most commonly used number system outside the digital world, that is in our day-to-day life. Okay, so this means that there will be a situation where decimal values have to be converted to binary values before they are entered into the digital system. Because, for example, if I buy large number of items, the shopkeeper will need calculator. So calculator need to operate in binary level. So what is the requirement? The digital system, so digital number system or decimal number system need to be converted into the binary one. So here is the example. For example, when you punch a decimal number into your hand calculator or computer, the circuitry inside the device converts the decimal number to binary value because it does not operate or it does not recognize decimal number. It has to convert it into binary. After that, it can perform the various calculation. Likewise, there will be a situation where the binary values at the outputs of the digital circuits have to be converted to decimal values for presentation to the outside world. So what it says that, for example, I want to perform, let's for simplicity, I want to add two number 10 and 2. So I will give input as decimal to the calculator. It will change it into binary, it will perform calculation, and after that it cannot provide me the answer in binary. So what it need to do is it need to convert the answer which is in binary to decimal and provide me the answer as 12 in decimal format. So for example, your calculator uses binary numbers to calculate the answer to a problem, then converts the answer to decimal before displaying them. The octal, that is base 8, hexadecimal, that is base 16, and the number system are both used for the same purpose to provide an efficient means for representing binary numbers. So what does it means that, for example, so what we let's suppose this is the given binary number. So it's quite large and we are unable to memorize this number. So to compress the binary number, we have two different number system. One is octal. So octal is the group of three binary bits. So it will combine three binary bits to give one octal digit so that the length of the number will be reduced and we can easily memorize it. In the same way, there is another number system, hexadecimal. It is also used to compress the binary number. So it will group four binary bits and it will compress it and give one digit in hexadecimal number system. So 111 is equivalent to F in hexadecimal. We will talk about it later. You don't have to worry right now. So in short, these two number system, that is octal as well as hexadecimal, these two will provide an efficient means for representing large binary numbers by compressing them. Octal will compress three binary bits into one octal digit, and hexadecimal will compress four binary bits into one hexadecimal digit. Okay, now let's start with the first number system, which is decimal number system. The decimal system is composed of 10 numbers. That is the reason it has base 10. So any number system whose base is n, it means that there are n different symbols to represent the numbers. In case of decimal, its base is 10, so it has 10 numerals or symbols to represent any quantity. These 10 symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8 up to 9. Using these symbols as digits of numbers, we can express any quantity in decimal number system. The decimal system also called the base 10 system because it has 10 digits and evolved naturally as a result of fact that man has 10 fingers. As you can clearly see that digit in Latin means the finger. So it originates from there. Okay, now let's go to the second point. The decimal system is a positional value system in which the value of the digit depends upon its position. For example, so if let's suppose there is number 453 in decimal, so position will give its value. So 4 is in 100 position, 5 is in 10th position, 3 is in unit position. So this 4 will carry the larger value. So we have 400, 5 tenths and 3 units. In essence, 4 carries the most weight as it is 400 of the 3 digits. It is termed as most significant digit. So right one digit is most significant digit because it will carry larger value. In the same way, the left side digit in the given case, which is 3, it is called as least significant digit, LSD, because it will carry the least value or least weight. Consider another example. Suppose there is decimal point in between the numbers. So let's consider 27.35. So it is equal to 2 tenths, 7 units, 3 tenth, 3 divided by 10. In the same way, 500, 5 divided by 100. So which is equivalent to 2 into 10 plus 7 into 1 plus 3 into 0.1 plus 5 into 0.01. The decimal point is used to separate integer part and the fractional part. So the part which is on the right hand side of the decimal digit is integer part, this is integer part, and the part which is on the which is on the right hand side, it is fractional part, and which is on the left hand side, it is the integer part. So this is the integer part. So 27 is the integer part and 35 is the fractional part in the given case. Okay, so let's go through another example. So 2745.214 actually is the abbreviated form of this. That is, it is 2 into 10 to the power 3, 7 into 10 to the power 2, 4 into 10 to the power 1, 5 into 10 to the power 0, 2 into 10 to the power minus 1, 1 into 10 to the power minus 2, and 4 into 10 to the power minus 3. That is, if you sit here in the decimal point, on the left hand side you will have the increasing positive power of 10, and in the right hand side you have increasing but in negative form the positive power of 10. So here is 10 to the power minus 1, minus 2, minus 3, minus 4, and so on. In the left hand side you can see that it starts from 10 to the power 0, 1, 2, 3, 4, and so on. In general, any number is simply the sum of product of each digit and its positional value multiplied by its positional value. So you can clearly see that. So it is 2, its positional value is 10 to the power 3. So it is equivalent to 2 into 10 to the power 3. And again, sum of 7 into 10 to the power 2, again sum of 4 into 10 to the power 1, again sum of 5 into 10 to the power 0, again sum of 2 into 10 to the power minus 1, again sum of 1 into 10 to the power minus 2, and again sum of 4 into 10 to the power minus 3. So it is the sum of digits and its positional value that will represent the number. Unfortunately, the decimal number system does not lend itself to convenient implementation in digital system. I will go through one example, don't worry. It is very difficult to design electronics equipment so that it can work with 10 different voltage level. So why is it so? I will give you one example. Let's suppose we have 10 voltage to represent digits. So in case of decimal, there are 10 different representation. So 1 volt, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you can clearly see that. So it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is 10 volt. So these are the voltage level in which I have to represent the digit. So let's suppose it represents 0, it represents 1, 2, 3, 4, 5, 6, 7, 8, and 9. So now let's suppose. So Voltage level from 0 volt to 1 will represent the number 0, and voltage level from uh, 1 volt to 2 volt. Here you can see that these are the voltage level, and the voltage level from 1 to 2 will represent digit 1, and 2 to 3 will represent digit 2, and so on. So let's consider one scenario. So if there is error during transmission, okay, and there is error of 1 volt. So let's suppose I am transmitting the digit 8 and at a voltage level of, let's suppose, 8.5. If there is fluctuation of 1 volt, it will either become 7.5 or it will become 9.5. You can clearly see that even the 1 volt fluctuation will alter my message. So 8 will become 7 and or it can become 9. But if, let's suppose, I use binary number system, so I have just two levels, so I can divide my voltage up to 5 volt, then 10 volt. This will represent 0 and this will represent 1. Now 1 volt fluctuation won't cause as much problem as is caused in decimal number system, as you can clearly see. So I am transmitting, let's suppose, 1 in 7 voltage, let's suppose. So 1 volt fluctuation either goes to 6 volt, which is okay, or it can move or up to 8 volt, which is also okay. So you can clearly see that there is not any kind of problem or not so big problem as in comparison to decimal number system in binary number system. That is the reason digital devices today prefer binary number system over decimal number system. So this is the reason. Although the first generation of the digital devices are implemented in digital concept, that is in decimal number system. Okay, so for this reason, almost every digital system uses binary number system base 2 as the basic number to design electronic circuit that operate only in two voltage levels, as we have clearly discussed with the help of one example. Okay, so another number system that is most important and most frequently used in decimal number digital devices is binary number system. In binary system, there are only two symbols or possible digit values, 0 and 1. So its base is 2. So there are two symbols, that those are 0 and 1. Even so, this base 2 system can be used to represent any quantity that can be represented in decimal or other number system. Though there are only two different symbols, but it can represent all the quantities which are used in decimal or other number system. All the statements made earlier concerning the decimal system are equally applicable to binary number system too. That is, positional value and other concept are also applicable to binary number system. The binary system is also a positional value system where in each binary digit has its own value or weight expressed as a power of 2. In decimal number system, base is 10, so we have used the power of 10, but in case of binary number system, base is 2, so we will be using the power of 2 for calculating the positional values. Let's go through one example. So let's suppose this is the given binary number 1011.101. So as like the decimal, we will start from this binary point, and while going to the left, the power of the binary, power of 2 will increase. So it will start from 2 to the power 0, 2 to the power 1, 2 to the power 2, and it is 2 to the power 3. And in the same way, while moving to the right, it will be 2 to the power minus 1, minus 2, and minus 3. So for getting the number, again we have the same concept. So it will be 1 into 2 to the power 3 plus 0 into 2 to the power 2 plus 1 into 2 to the power 1 plus 1 into 2 to the power 0 plus 1 into 2 to the power minus 1 plus 0 into 2 to the power minus 2 plus 1 into 2 to the power minus 3. So the concept is same as like decimal number system. So positional value concept also applies to binary number system too. In the binary system, the term binary digit is often abbreviated as bit. So the symbols that are used in binary are termed as bit. So in decimal they are called as digit, but in case of binary they are called as binary digit. In short form, it is called as bit. So 0 and 1, these are the bits, not the digits. It's general concept. Okay, so next number system is octal number system. So its base is 8, which means that it has 8 different symbols to represent the number. That will start from 0 to 7. That is 0, 1, 2, 3, 4, 5, 6, and 7. There are only 8 possible digit values to represent a number. With the help of only 3 bits, an octal number is represented. It is also known as base 8 number system. That is, the maximum value of octal digit is 7. So you can clearly see that there are 8 representation in octal. Now let make me clear about this point. Only 3 bits are required. So we have one formula, that is number of representation required. Let's suppose this is the number of representation required. Let's suppose it is x. Let's suppose it is x. So how many bits are required can be calculated with the help of this formula, where x is the number of representation required. So you can clearly see that in case of octal, the value of x is 8. And while solving this, we can see that the value of n will be 3. So we will need 3 bits to represent any octal number because there are 8 representation. In the same way, we can calculate for hexadecimal number system too. So in case of hexadecimal number system, the value of x will be 16 because there are 16 different representation, and solving this equation we will get the value of n as 4. So we will need 4 binary bits to represent hexadecimal number. Let's suppose there are other representation. Let's suppose there is one representation that use 64 different representation. Uses 64 different representations. So you have to go for you have to simplify this. So you can calculate 2 to the power 1 is 2, then 4, 8, 16, 32, 64. So whenever you get 2 to the power 6, when you calculate 2 to the power 6, you will get 64. 2, 4, 8, 16, 32, 64. That is 2 to the power 6 is 64. So if we need 64 different representation, the number of bits that we need is 6. So this is the simple formula, and it will be reused again and again. You have to be very clear about it. Okay, now let's talk about our final number system, which is hexadecimal number system. So its base is 16. So it will be using 16 different symbols. So we have 10 symbols up to 9, and for representing other number, that is 10, 11, 12, 13, 14, and 15, we have these alphabets. So A will be 10, B will be 11, 12, 13, 14, and 15. Okay, so we will be using some alphabets in hexadecimal number system. The single bit representation of decimal values 10, 11, 12, 13, 14, and 15 are represented by these alphabets. Only 4 bits are required for representing a number in hexadecimal number. Each set of bits has a distinctive value from 0 to 15. So we need how many bits? 4 bits. Why 4 bits? Because 2 to the power 4 is equals to 16, and there are 16 different representation in, or 16 different symbols in hexadecimal number system. That is the reason we need 4 bits. So these are the examples. So see, as there is base 16, we can clearly call them as hexadecimal number. Okay, so here is the summary of the numbers. Let's go through it. So let's start with hexadecimal number. That will be easy. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After that we have A, B, C, D, E, and F. Okay. Now the corresponding value in octal can be obtained as 0, 1, 2, 3, 4, 5, 6, 7. So 7 is equivalent to 7. Now there is no 8 in octal number system. So after 7 there will be 1 0. Then it will be again 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 1 7, and it's done. After that it will be 2 0 because we don't have 1 8. Now let's talk about decimal. Okay, so here with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and after that it will be 1 0 1 1 1 2 1 3 1 4 1 5 1 6 and so on. We are very much familiar about this. In case of binary, so what we have is we will be altering this digit once. So 0 0 0, this is our first representation. After that we will have 0 0 0 1. We have altered this, so we will alter now second digit. So it will be 0 0 1 0, again 0 0 1 1. Now we have altered this too. Now we will be altering this. So 1 0 0, and again the pattern will be repeated. I will be teaching you the shortest way to write this representation. Just focus on that. Okay, shortest way. Now look. So it's very simple. So it will be altered only once. It will be altered twice. It will be altered 4 times. It will be altered in 8 times. So it's very simple notation. So this is the first number. So every case what you need to do is you need to alter this after 8 times. So you have to write 8 0. 1 2 3 4 5 6 7 8. Now it will be changed to 1 1 2 3 4 5 6 7 8. I will be using lines to differentiate. Okay, so you don't have to memorize. You can write it by simple concept when to alter the number. Just you have to know that. Now it is very important concept and we will be using this rapidly, so you need to be very familiar about it while writing the possible values. So what you need to do is maximum number of bits that we will be dealing is 4. So MSB, it should be altered after 8 values, it should be altered after 4 values, it should be altered after 2 values, and it should be altered after 1 value. So 4 0 1 2 3 4, again 4 1 1 2 3 4, again 4 0 1 2 3 4, again 4 1 1 2 3 4. Now alter it in 2 steps. So 2 0 2 1 2 zeros, again 2 1 2 zeros, again write 2 1, next 2 zeros, again 2 1, and it is altered in every step. 0 1 0 1 0 1 0 1 0 1 0 1 0 1 and 0 1. So we will get the equivalent value. So it is decimal 0, it is decimal 1 2 3 4 5 6 7 8 9 10 11 12 13 14, and it is 15. So in this way, without memorizing, we can write the values. So it will apply to all the possible combination, and in case of our syllabus, the maximum number of binary bits that we are dealing is 4. So you have to memorize this. If we need to write possible values of 3 binary bits, so what you need to do is you need to alter 4 times, alter after 2 times, alter after 1 time. So what will be the possible values? We will start from this 0. So 4. So 4 0, 4 1. After that 2 0, 2 1, 2 0, 2 1, and alter in every step. 0 1 0 1 0 1 0 1. In this way you can write the possible values of various number of bits. Okay, now let's go back to the previous table. So this is the table. So that's it for today's lecture. I will be going with the conversion of the number system in the coming lectures. Thanks for watching.